Today, we officially begin our first major lesson in tropical design, which focuses on the foundations of tropical architecture. This module is extremely important because it establishes the environmental, theoretical, and historical framework of the entire course. Before architects can design climate responsive buildings, they must first understand the relationship between architecture and climate. The topics we will discuss today includes principles of tropical design, climate responsive architecture, tropical environmental conditions, Philippine climatic zones, and tropical architectural history. These topics are interconnected because architecture in tropical regions cannot be separated from environmental realities. Throughout history, architecture evolved according to climate. Buildings developed differently depending on temperature, rainfall, sunlight, wind conditions, available materials, and human survival needs. In tropical countries like the Philippines, architecture faces unique environmental challenges such as excessive heat, high humidity, heavy rainfall, typhoons, flooding, and intense solar exposure. Therefore, architects must design buildings that respond intelligently to these conditions rather than ignore them. This module will help us understand how environmental responsiveness influences architectural form, spatial organization, material selection, and human comfort. Let us begin by defining tropical architecture. Tropical architecture refers to architectural design specifically developed to respond effectively to hot, humid, and tropical climatic conditions. One important thing to understand immediately is that tropical architecture is not merely a visual style. Many people incorrectly assume that tropical architecture only refers to resort aesthetics, wooden finishes, large glass openings, minimalist tropical interiors, and luxury vacation houses. However, authentic tropical architecture is fundamentally about environmental performance. Its main objective is to create comfortable and sustainable spaces that respond appropriately to climate while minimizing dependence on artificial systems such as air conditioning. This means tropical architecture focuses heavily on natural ventilation, solar protection, heat reduction, moisture management, daylighting, and passive cooling. Tropical architecture seeks to work with nature rather than against it. In tropical climates, environmental conditions significantly affects human comfort. If buildings are poorly designed, occupants experience excessive indoor heat, poor ventilation, moisture problems, mold growth, high energy consumption, and uncomfortable living conditions. Therefore, tropical architecture becomes both an environmental and human centered design approach. One of the most important concepts in tropical design is this: climate shapes architecture. Climate is one of the oldest and most powerful determinants of architectural form throughout human history. Different climate produce different architectural solutions because buildings must respond to environmental conditions in order to support human survival and comfort. For example, cold climates prioritize heat retention. Desert climates prioritize thermal mass and shading. Tropical climates prioritize ventilation and heat dissipation. This means architecture cannot be universal or generic. Good architecture responds specifically to environmental context. In tropical regions, climate almost every architectural decisions, including orientation, building shape, roof configuration, window placement, material selection, spatial organization, and landscape integration. For instance, a building facing intense western sunlight may experience severe heat gain during the afternoon. Architects therefore design shading systems and orientations that reduce unwanted solar exposure. Similarly, natural airflow patterns influence how windows and spaces are organized. Buildings that maximize airflow can significantly improve comfort naturally. Therefore, climate responsive design begins with environmental understanding. Before designing aesthetically, architects must first understand how buildings behave environmentally. To design effectively within tropical regions, architects must first understand the environmental characteristics of tropical climates. Tropical climates are generally characterized by warm temperatures throughout the year, high humidity, significant solar radiation, intense rainfall, and seasonal wind patterns. These conditions create several architectural challenges. First, high temperatures increase heat gain within buildings. If poorly designed, interiors become uncomfortable and heavily dependent on mechanical cooling systems. Second, high humidity creates moisture related problems such as condensation, mold growth, material deterioration, and reduced thermal comfort. Third, strong solar radiation significantly affects indoor temperatures. Sunlight striking walls, roofs, and glass surfaces transfers heat into the interior spaces. Heavy rainfall and tropical storms also require architects to carefully consider roof design, drainage systems, waterproofing, structural resilience, and flood protection. In the Philippines, specifically, environmental challenges become even more complex because of frequent typhoons, flooding, coastal exposure, urban heat island effects, and therefore, tropical architecture must become environmentally adaptive and resilient. One of the primary objectives of tropical architecture is achieving thermal comfort. Thermal comfort refers to the condition where the occupants feels physically comfortable within an environment. Human comfort depends on several environmental factors, including air temperature, humidity, air movement, surface temperatures, and solar exposure. In hot, humid climates, humidity becomes one of the most important issues because high humidity reduces the body's ability to cool itself through perspiration. This is why ventilation is extremely important in tropical architecture. Air movement improves comfort significantly even when temperatures remain relatively warm. Architects therefore design tropical buildings that encourages cross ventilation, natural airflow, heat dissipation, and reduce solar heat gain. One major misconception today is that thermal comfort can only be achieved through air conditioning. However, traditional tropical architecture achieved comfort long before mechanical cooling systems existed. Through intelligent environmental design, buildings themselves can improve human comfort naturally. This is one of the major philosophies behind climate responsive architecture. Now, let us discuss the core principles of tropical design. These principles serve as the foundation for environmentally responsive architecture within tropical regions. The first principle is climate responsiveness. Tropical architecture must respond directly to environmental conditions rather than ignore them. Every design decision should consider climate. The second principle is passive cooling. Passive cooling refers to strategies that reduce heat naturally without depending heavily on mechanical systems, such as air conditioning. Examples include cross ventilation, stack ventilation, shading systems, proper orientation, reflective materials, and vegetation integration. The third principle is natural ventilation. Because tropical climates are humid and warm, airflow becomes essential for improving thermal comfort. The fourth principle is solar protection. Tropical regions experience intense solar radiation throughout the year. Architects therefore use roof overhangs, vertical fins, louvers, screens, vegetation to minimize excessive heat gain. Another important principle is environmental integration. Tropical architecture should work harmoniously with the landscape, site conditions, topography, and natural ecosystems. Finally, sustainability and human-centered design remain central goals. Good tropical architecture minimizes environmental impact while improving human comfort and well-being. One of the defining characteristics of tropical architecture is the use of passive cooling strategies. Passive cooling refers to architectural methods that reduce indoor heat naturally without excessive energy consumption. The first strategy is cross ventilation. This occurs when air enters through one opening and exits through another, creating airflow across interior spaces. Properly designed cross ventilation improves thermal comfort, air quality, heat removal, and occupant well-being. Another important strategy is the stack effect. Warm air naturally rises. Architects use these principles by creating higher openings that allows hot air to escape while cooler air enters lower openings. Shading devices are also extremely important in tropical climates. This includes roof overhangs, louvers, vertical fins, brise soleil, and pergolas. Their purpose is to minimize unwanted solar heat gain. Traditional tropical architecture often utilized elevated floors. Elevated structures improves air circulation, flood protection, and moisture control. Courtyards are another passive cooling strategy because they create shaded microclimates and encourage airflow movement. Vegetation also contributes to cooling through shading and evapotranspiration. These strategies demonstrate how architecture itself can function environmentally.
Natural ventilation is one of the most important environmental strategies in tropical design. Ventilation refers to the movement of air through spaces. In tropical climates, ventilation performs several important functions: removes indoor heat, reduces humidity, improves air quality, enhances occupant comfort. There are different types of natural ventilation. The first is cross ventilation, where air flows horizontally across spaces through properly positioned openings. Cross ventilation works best when openings are aligned with prevailing winds, interior obstructions are minimized, spaces allow airflow continuity. The second type is stack ventilation. Warm air rises naturally because it becomes less dense. Architects use vertical spaces such as atriums, clear stories, or roof vents to release hot air upward. Single sided ventilation occurs when air enters and exits through openings on the same side. This is generally less effective than cross ventilation. Ventilation design is highly dependent on building orientation, wind direction, opening placement, interior layout. Traditional tropical architecture demonstrates excellent examples of natural ventilation strategies. One of the greatest environmental challenges in tropical regions is excessive solar heat gain. When sunlight strikes buildings, surfaces absorb heat and transfer it indoors. This significantly affects thermal comfort and increases energy demand. Architects therefore develop solar control strategies to minimize unwanted heat gain while still allowing natural light into spaces. One of the most common shading devices in tropical architecture is the roof overhang. Large overhangs protect walls and openings from direct sunlight and rainfall. Louvers and screens are also widely used because they allow airflow while filtering sunlight. Vertical fins are effective for controlling low angle sunlight, especially from eastern and western exposures. Vegetation serves as another important shading strategy. Trees and plants reduce surrounding temperatures while creating cooler microclimates. Good solar control improves indoor comfort, energy efficiency, daylighting quality, building durability. This demonstrates how environmental analysis directly influences architectural form. Building orientation is one of the most important decisions in tropical design. Orientation refers to how buildings are positioned relative to the sun, prevailing winds, site conditions, environmental context. Proper orientation significantly improves environmental performance. For example, in tropical climates, minimizing Western solar exposure is extremely important because Western sunlight generates intense afternoon heat. Architects therefore carefully position walls, windows, openings, outdoor spaces to reduce unwanted heat gain. Orientation also affects ventilation. Buildings positioned according to prevailing wind directions can maximize natural airflow. Good orientation improves thermal comfort, energy efficiency, daylighting, ventilation performance. Poor orientation, however, creates overheated interiors, high cooling loads, uncomfortable spaces, increased operational costs. This is why environmental analysis should occur during the earliest stages of architectural design. Landscape and vegetation are extremely important components of tropical design. Plants and trees are not merely decorative features, they perform major environmental functions that improve thermal comfort and environmental quality. Vegetation contributes to shade creation, cooling, heat reduction, air quality improvement, stormwater absorption. Trees reduce surface temperatures significantly by blocking direct solar radiation. Plants also cool surrounding air through evapotranspiration, which releases moisture into the atmosphere and lowers ambient temperature. Landscape design can also guide airflow and create comfortable outdoor spaces. Another important function of vegetation is stormwater management. Tropical regions experience intense rainfall, so landscapes help absorb and slow down water runoff. Good tropical architecture therefore integrates buildings with natural systems rather than separating them from nature. Now we move into one of the most important concepts in this course: climate responsive architecture. Climate responsive architecture refers to architectural design that directly responds to environmental conditions and climatic behavior. Instead of forcing buildings to resist climate through excessive mechanical systems, climate responsive architecture works with environmental conditions intelligently. The primary goals of climate responsive design include reducing energy consumption, improving thermal comfort, enhancing environmental performance, promoting sustainability, minimizing ecological impact. This approach is especially important today because many modern buildings consume excessive energy due to poor climatic design. Buildings that ignore climate often require heavy air conditioning, artificial lighting, mechanical ventilation, continuous energy consumption. Climate responsive architecture attempts to minimize these dependencies through intelligent environmental design. In tropical regions, climate responsive architecture often includes proper orientation, natural ventilation, shading systems, vegetation integration, passive cooling, moisture management. This approach recognizes that architecture is not isolated from nature. Buildings continuously interact with environmental forces such as heat, wind, sunlight, rainfall, humidity. Architects, therefore, must design with environmental awareness. Climate responsive design follows several important environmental principles. The first principle is site sensitivity. Every site possesses unique environmental conditions. Architects must analyze solar orientation, wind direction, topography, vegetation, rainfall behavior, existing environmental systems before designing. The second principle is environmental analysis. Climate responsive architecture depends heavily on scientific understanding rather than assumptions. Architects use environmental tools to study sun paths, wind patterns, thermal comfort, environmental performance. Another major principle involves passive environmental systems. Buildings should improve comfort naturally through ventilation, shading material behavior. Spatial organization solar control is also critical. Since tropical regions receive intense sunlight, architects must reduce excessive heat gain while maintaining daylight quality. Ventilation optimization remains another important strategy because airflow significantly improves thermal comfort in hot, humid environments. Sustainable material selection also contributes to environmental responsiveness. Materials influence heat absorption, moisture behavior, durability, environmental impact. Finally, ecological integration emphasizes harmony between architecture and natural systems. Good climate responsive architecture behaves as part of the environment rather than as an isolated object. One of the most important historical lessons in tropical design is this: traditional architecture achieved environmental comfort long before air conditioning existed. For thousands of years, human civilizations developed climate responsive architecture through observation, experience, and adaptation. Traditional tropical architecture demonstrates remarkable environmental intelligence. Examples include Bahay Kubo in the Philippines, Malay houses, Balinese compounds, Southeast Asian vernacular dwellings. These buildings incorporated several passive environmental strategies such as elevated flooring, lightweight materials, open floor plans, cross ventilation, large roof overhangs, permeable walls, elevated floors, improved air circulation, moisture protection, flood resilience, wide roof overhangs, protected interiors from rainfall, solar heat gain, lightweight materials, responded quickly to temperature changes, and reduced heat retention. These traditional systems demonstrate that environmental responsiveness existed long before modern sustainability movements emerged. Modern architects can learn significantly from vernacular architecture because many traditional buildings were highly optimized for climate. One of the best examples of climate responsive architecture in the Philippines is the Bahay Kubo. The Bahay Kubo evolved specifically according to tropical environmental conditions and local cultural practices. Its elevated structure protects against flooding moisture ground heat pests. At the same time, the elevated flooring allows airflow beneath the structure, which improves cooling. The steep roof efficiently drains heavy tropical rainfall while also helping release accumulated heat. Large openings and permeable wall systems encourage natural cross ventilation. Traditional materials such as bamboo, nipa wood, rattan possess environmental advantages because they are lightweight and breathable. The Bahay Kubo demonstrates that architecture can achieve comfort naturally through environmental adaptation rather than technological dependence. This traditional architecture remains highly relevant today because many of its environmental strategies align with modern sustainable design principles. Vernacular architecture refers to traditional architecture developed by local communities using locally available resources and environmental knowledge. Vernacular buildings are highly important in tropical design because they demonstrate generations of environmental adaptation. Unlike many modern buildings driven primarily by aesthetics or commercial trends, vernacular architecture evolved according to climate materials culture, survival needs, environmental conditions. This makes vernacular architecture highly sustainable and environmentally responsive. Common characteristics include local materials, passive cooling systems, climate adaptation, resource efficiency, community centered spaces. In tropical regions, vernacular architecture often prioritizes ventilation shading, rain protection, flexible spaces, environmental integration. Studying vernacular architecture is important because it teaches architects how traditional communities solved environmental problems intelligently using simple but effective strategies. Modern sustainable architecture frequently reinterprets vernacular principles using contemporary technologies and materials. Modern tropical architecture combines traditional environmental principles with contemporary technologies and construction systems. Today's tropical buildings increasingly integrate sustainable materials, passive environmental systems, smart technologies, energy efficient systems, ecological planning. One major feature of modern tropical architecture is indoor outdoor integration. Tropical climates often allow closer relationships between interior and exterior spaces. Architects therefore design open layouts, courtyards, transitional spaces, shaded terraces, semi outdoor environments. Modern tropical architecture also emphasizes environmental performance. Buildings are now analyzed according to energy consumption, thermal comfort, daylighting, airflow performance, carbon footprint. Contemporary tropical architecture seeks to combine environmental intelligence, technological advancement, human comfort, sustainability, cultural sensitivity. This demonstrates that tropical design continues evolving in response to modern environmental challenges. While traditional tropical architecture solved many environmental problems naturally, contemporary cities now face much more complex environmental challenges. Today, architects must respond not only to climate, but also to rapidly changing urban conditions. One major issue is climate change. Rising temperatures and increasingly unpredictable weather patterns are affecting cities globally. In tropical countries like the Philippines, climate change contributes to stronger typhoons, more severe flooding, rising temperatures, coastal vulnerabilities, increased environmental stress. Another major issue is the urban heat island effect. Cities become significantly hotter because of concrete surfaces, asphalt roads, glass buildings, reduced vegetation, dense urban development. As cities expand rapidly, many developments ignore environmental responsiveness. Buildings become dependent on excessive air conditioning and artificial systems. This increases energy consumption, carbon emissions, operational costs, environmental degradation. Flooding also becomes more severe because urbanization reduces permeable ground surfaces and natural drainage systems. Architects today therefore carry greater responsibility. Contemporary tropical architecture must address sustainability, climate resilience, energy efficiency, ecological balance, human well being. This means tropical design is no longer optional, it is becoming essential for future architectural practice. The Philippines possesses multiple climatic zones, and understanding these climatic variations is extremely important for architects. According to Pagasa, the Philippines is divided into four major climatic types based on rainfall distribution and seasonal weather behavior. Type 1, climates experience distinct dry and wet seasons. Type 2, climates experience no dry season, very pronounced rainfall periods. Type 3, climates experience intermediate rainfall conditions. Type 4, climates experience relatively even rainfall distribution throughout the year. These climatic differences affect architectural decisions significantly. For example, regions with strong typhoon exposure may require stronger structural considerations and more protective roofing systems. Areas with intense rainfall may require larger roof overhangs, better drainage systems, elevated flooring, moisture resistant materials. Similarly, regions with stronger solar exposure may require enhanced shading and ventilation strategies. This demonstrates that climate responsive architecture must always respond specifically to local environmental conditions rather than applying generic solutions everywhere. Wind systems are another extremely important environmental factor in tropical design. In the Philippines, two major monsoon systems strongly influence environmental conditions. Amihan Habagat. Amihan refers to the northeast monsoon, which usually brings cooler temperatures, dry air, strong northeasterly winds. Habagat refers to the southwest monsoon, which often brings warm, humid air, heavy rainfall, storm conditions. Architects must understand these seasonal wind behaviors because wind directly affects ventilation, thermal comfort, moisture behavior, rain penetration, building performance. For example, buildings positioned according to prevailing wind directions can maximize natural airflow and improve indoor comfort. However, architects must also protect buildings from strong wind driven rainfall during monsoon seasons. This requires careful consideration of opening placement, roof design, window protection, building orientation. Spatial organization, traditional tropical architecture often demonstrates sophisticated responses to seasonal wind patterns. Tropical architecture has evolved continuously throughout history according to changing environmental, cultural, and technological conditions. The earliest forms of tropical architecture emerged from indigenous communities adapting to local environmental realities using available resources. These early structures emphasized ventilation, flood protection, lightweight construction, environmental integration. As societies developed, vernacular architecture evolved according to climate, culture, religion, technology, local materials. Colonial influences later introduced new architectural forms and construction methods into tropical regions. In the Philippines, Spanish colonial architecture incorporated thick masonry walls, capiz windows, ventanilas courtyards, large roof overhangs. These adaptations combined foreign architectural influences with tropical environmental responses. During the 20th century, architects began developing modern tropicalism, which merged modernist architecture with climate responsive principles. Today, contemporary tropical architecture continues evolving through sustainability, green technologies, environmental simulations, climate resilience, smart systems. This historical evolution demonstrates that architecture constantly adapts according to environmental realities and societal changes. Modern tropicalism emerged as an architectural movement that attempted to reconcile modern architecture with tropical environmental conditions. Many early modernist buildings ignored climate and relied heavily on mechanical systems. As a response, architects began developing modern tropical approaches that combined modern aesthetics, environmental responsiveness, regional identity, passive environmental systems. One major figure associated with modern tropicalism is Geoffrey Bawa from Sri Lanka. Bawa's architecture emphasized landscape integration, open spatial planning, natural ventilation, environmental harmony, indoor outdoor relationships. Another influential architect is Ken Yang, who focused on ecological skyscrapers and bioclimatic architecture. Modern tropicalism demonstrates that contemporary architecture can remain technologically advanced while still respecting environmental conditions. This movement continues influencing tropical architecture today because climate responsive design has become increasingly important globally. Before we conclude today's discussion, let us synthesize the major concepts we learned. First, climate is one of the most important determinants of architecture. Buildings must respond appropriately to environmental conditions. Second, tropical design is fundamentally about environmental responsiveness rather than purely aesthetics. Third, passive environmental systems remain essential in achieving thermal comfort naturally and sustainably. Fourth, traditional and vernacular architecture provide valuable lessons in climate adaptation and environmental intelligence. Finally, sustainability and climate responsiveness are becoming increasingly important in contemporary architectural practice. As future architects, your challenge is not simply to create visually impressive buildings, but to design architecture that improves human comfort, conserves energy, responds to climate supports, sustainability, respects environmental systems. These foundational concepts will guide the rest of our course throughout the semester. To end today's lesson, let us reflect critically on the topics discussed. Architecture is not isolated from environmental realities. Therefore, architects must constantly evaluate how buildings affect both people and the environment. I want you to think deeply about the following questions. Why should climate influence architecture? Why do many contemporary buildings still ignore environmental responsiveness? What valuable lessons can modern architects learn from traditional architecture? How will climate change transform future architectural practice? These questions are important because architecture today faces environmental responsibilities that previous generations may not have experienced at the same scale. As future architects, your role extends beyond aesthetics and construction. You will help shape how society responds to environmental challenges through design. Let us now compare traditional tropical architecture and modern tropical architecture. Although they belong to different historical periods, both approaches share many environmental objectives. Traditional tropical architecture relied heavily on local knowledge, vernacular materials, environmental adaptation, passive systems. Buildings such as the Bahay Kubo achieved comfort naturally through cross ventilation, elevated flooring, lightweight construction, roof overhangs. Modern tropical architecture, on the other hand, integrates contemporary materials, smart technologies, environmental simulations, advanced engineering systems. However, despite technological advancements, many environmental principles remain the same. Both traditional and modern tropical architecture aim to improve thermal comfort, reduce heat gain, encourage ventilation, respond to climate, enhance environmental performance. This comparison demonstrates an important lesson. Good architecture evolves technologically, but environmental principles remain fundamentally important. Unfortunately, many contemporary buildings still fail environmentally because they ignore tropical climatic realities. One common mistake is excessive use of glass facades without proper shading systems. While glass may appear modern aesthetically, large unprotected glass surfaces in tropical climates create excessive heat gain, thermal discomfort, increased cooling loads, higher energy consumption. Another major issue is poor ventilation planning. Buildings that fail to encourage airflow become dependent on mechanical cooling systems. Improper orientation also creates environmental problems. Structures exposed directly to harsh western sunlight often overheat significantly during afternoons. Minimal shading, excessive concrete exposure, and poor material selection further worsen environmental performance. Many developments today prioritize appearance over climatic responsiveness. As future architects, it is important to avoid designing buildings that merely look impressive visually but perform poorly environmentally. Good architecture should balance aesthetics, functionality, sustainability, comfort, environmental responsiveness. Environmental intelligence should always guide design decisions. Tropical design and sustainability are deeply interconnected. Sustainability refers to meeting present needs without compromising future generations' ability to meet their own needs. Buildings significantly affect energy consumption, carbon emissions, resource use, environmental degradation. Therefore, architects play a major role in sustainable development. Climate responsive tropical architecture contributes to sustainability through passive cooling, reduced energy demand, natural lighting, environmental integration, resource efficient materials. For example, buildings with proper ventilation and shading require less air conditioning, which reduces electricity consumption. Similarly, daylighting strategies reduce dependence on artificial lighting. Sustainable tropical architecture also considers water conservation, ecological balance, material sustainability, climate resilience. This demonstrates that tropical design is not merely aesthetic, it is part of global environmental responsibility. The future of tropical architecture is becoming increasingly innovative and technologically advanced. As environmental challenges intensify, architects must develop more intelligent and adaptive design solutions. One emerging direction is smart tropical buildings, which use sensors and automation to optimize environmental performance. AI assisted environmental analysis is also becoming increasingly important. Artificial intelligence can now help architects analyze climate data, predict environmental performance, optimize building orientation, improve energy efficiency. Another major direction is net zero architecture, where buildings aim to produce as much energy as they consume. Biophilic design is also gaining importance. This approach strengthens connections between people and nature through vegetation, natural light, and environmental integration. Climate resilience will remain a major priority because future buildings must withstand Rising temperatures, extreme rainfall, stronger storms, flooding, environmental uncertainty. The future architect must therefore become technologically informed, environmentally responsible, research driven, sustainability oriented. Tropical design will continue evolving as environmental challenges evolve. Let us summarize the major concepts we learned throughout weeks 1 and 2. First, climate is one of the most important determinants of architecture. Environmental conditions strongly influence building form, orientation, materials, and spatial organization. Second, tropical design is fundamentally climate responsive. It aims to improve comfort while minimizing environmental impact. Third, passive environmental systems remain critical in tropical architecture because they reduce dependence on mechanical cooling systems. Fourth, vernacular and traditional architecture provide highly valuable lessons in environmental adaptation. Fifth, sustainability is now inseparable from tropical architectural practice. Finally, architects today must become environmentally aware professionals capable of addressing climate related challenges through intelligent design solutions. These foundational principles will guide all succeeding lessons throughout the semester. In our next lesson, we will move from theoretical foundations towards scientific environmental analysis. We will begin learning how architects analyze climate using professional environmental tools such as sun path diagrams, wind rose charts, psychrometric charts, thermal comfort studies. These tools allow architects to make informed design decisions based on actual climatic data rather than assumptions. Understanding environmental analysis is essential because climate responsive architecture depends on measurable environmental behavior. As future architects, you must become capable of reading environmental conditions scientifically and translating them into intelligent design strategies. This concludes our discussion for weeks 1 and 2 on the foundations of tropical architecture.